kind of a recycled question here. A point on the domain of a function is a critical point if what one of two things happens. Okay. So you're saying the derivative is 0 or the derivative does not exist. Okay. And so today we're going to kind of recycle that critical point, that definition, okay? And we're going to kind of rename it, but we'll get to that in a second. So if we were to look at this graph here, and I would ask you to mark the critical points here. How many critical points do we have based on that definition? And where are they?
6. This is 5.
So how many critical points do we have? We have 5, and this says, where are they? Might be a stretch if you don't look at the bottom axis.
C1, C2, C3, C4, C5.
Yeah, C1, 2, 3, 4, and 5. Okay, so here are all my points where my derivative is 0. Do we have some hills? Do we have some valleys? Do we have a cusp or a corner? We've got examples of each. But we also have a couple other things, like that C1 point and this C5 point. We have a horizontal tangent, but do we have a hill or a valley or a cusp or a corner? What do we have there? Anyone want to venture to guess what that is right here? That's C5? Is it a hill? Is it a valley? So what? In real non-mathy terms, it's kind of a horizontal spot, right? Or sometimes we call those plateaus. It kind of flattens out, but it doesn't create like a hill or a valley. It just kind of comes down, flattens, and then continues down. Or in the case of C1, it comes up, flattens, and continues up. You know, we kind of come up here, we kind of flatten, and then we kind of continue up here. Or we come down here and flatten, and then we continue down here. So they're not mins or maxes, but they're these plateaus that still have horizontal tangents. Okay? So they still are kind of falling into that category of critical point by definition because the derivative is 0. Okay? So what we're going to do, since we're not really talking about strictly hills and valleys and cusps and corners anymore, we're going to start to rename the whole critical point task, or the finding of critical points. We're going to rename that to the first derivative test. So in other words, we're going to take the derivative of a function and we're going to test for when that derivative is equal to what? Exactly. We're going to test for when that derivative is equal to 0. Okay? And then we're going to look on either side and look and see, well, am I positive derivative, negative derivative? Okay, we're going to do those sort of things. So we've kind of, in this first bullet item here, we've kind of already done this. We're going to do it some more. Okay? And then we're going to make the table that we've made before in the past. Okay, we're going to make that table that summarizes where my critical points are, or summarizes the results of the first derivative test. And then we're going to see where my function is increasing and decreasing. Okay, so this is for increasing and decreasing function values. Okay? And then the new thing for today is we're going to talk about concavity or concavity, however you want to say that. Kind of like tomato. And the concavity, we'll talk about in a little bit what that means. But basically, now we're starting to look at the shape of the graph, not just if it's increasing or decreasing, it's going up or down, but what shape is it taking on? And that's going to help us sketch it. And so that's going to be kind of a new thing today. Is that getting that basic shape so that we can get a sketch. Okay? So any questions so far? Okay, so when we talk about the first derivative test, finding our critical points. Okay, it looks like a long test, but it's really pretty intuitive because we've been talking about it for some time now. Okay, we're talking about critical points being at mins or maxes. So here's my critical points that I could have as maximums. Here's my critical points I could have as minimums. And we've been working with those for a few days now. If we notice for mins and maxes, and this is getting into our table, our derivative changes sign. On one side of the max, we have a positive derivative, and on the other side of the max, we have a negative derivative. Right? We have our function increasing and then decreasing. So we're going up then coming down. If the derivative is positive, then it's negative. Okay? Because our derivative is that tangent line. So, so we have a definite change in the value of that slope. Same with our mins. We have a definite change in the value of that slope. The change reverses itself. So that gets talking about our table here. Okay, when we talk about that slope. Here are our plateaus now. Okay, so when we talk about this, notice we have a slope that's positive, it flattens, and then we continue in the positive direction. Okay, so if you think about that on a number line, positive value for slope here would be like being over here on the number lines in the positive numbers, right? And then my value for slope is going to flatten out and go to what value?
Students, if you participate in the jazz band, the wind ensemble, SWAP, concert band, or pep band, please report to the auditorium for your yearbook photo. Thank you.
Okay. When our slope flattens out, we have a value of what value? Zero, right? And so think about that on a number line. We have positive values of slope here. Our values for slope are going to go to 0 on the number line, and then they're going to go to what value? Back to positive. So on these plateaus, we see our slope go from here, bounce off 0, and come back that way for those plateaus. And then, so we still have positive slope here. Okay? So it goes from a positive value to flat to positive. It just kind of bounces off 0 and goes right back. So where these mins and maxes, we're seeing a sign change, here we're not at that critical point. So as we do that table, we would have a critical point, and then we have increasing on both sides of those critical points. Does anybody know of a function that does this? That flattens out like that in a spot and continues, either goes up, flattens and continues up, or maybe the other way. Goes down, flattens and continues down. Yep, I know you have. Somebody said, yeah, x to the third. Exactly. Right? If we look at f of x equals x cubed, it looks like this. Okay, so we have that plateau here, right? Our derivative is 3x squared. And so where's our derivative 0? Our derivative is 0 right here. So we know we have a horizontal tangent. We start out with a positive tangent, we flatten out to 0, and then we bounce off 0 and go back into the positive values for tangents again. Okay. In fact, any polynomial with what sort of power, like does x squared, would x squared have a plateau? Or does x squared have hills and valleys? Hills and valleys, right? X squared parabola.
Oh,
It's got hills or a valley. Okay. So what sort of powers on the polynomial give me the potential of having a plateau?
oh,
Odds, right? Yeah, our x cubed, x to the fifth. We have the potential of having plateaus there. Okay. And then we also talk about making sure that in terms of local mins and maxes, more so than zero derivatives, but we have to acknowledge that if we're at the end of an interval and we have a negative derivative, meaning we have a function that's going down, then that end has to be a local max. Or if we've got a positive derivative, then that end has to be a local min. So we always have those local extrema at the endpoints too. Okay? So local extrema at endpoints. Also, okay. Okay, so really we're just looking at this problem the way we looked at it yesterday. We're gonna use the first derivative test, and we're gonna find those critical points. So the first derivative test says take the derivative, set it equal to 0. So what's the derivative of this function up here? Okay, so 3x squared minus 3 equals 0. And I solve that, and what do I get? How do you want to solve that?
oh.
Okay. Now how do you want to solve that? Okay. Is there another way to solve this?
You could
Yeah, couldn't we do a square root thing here too? Because we only have x in one spot. Either or, it doesn't matter. Just if we do a square root thing, remember to take plus or minus. This, you can see the plus minus a little more easily. So we know we have those critical points. Because of the first derivative test. So we've got these critical points. Critical points means we've got 0 slope or undefined slope. If we've got a continuous function, it's not going to be undefined, it's going to be 0. Okay? We'll be dealing with these polynomial functions a lot. So let's go ahead and get these in the table then. So we're going to identify our critical points. X equals -1 and x equals 1. And we're going to see what happens in each region on either side of these critical points. So what happens when x is less than or equal to -1? We have a positive slope, right? Okay, and you can see that by drawing the tangent line on the graph. And we see we got a positive tangent line. If we didn't have the graph, what would we have to do? Yeah, we'd have to take our derivative, which is 3x squared minus 3, and test a point that's littler than negative 1. So if we test x equals negative 2 and put that in there, we get a positive slope. We get a positive value. And what does positive derivatives tell us? An increasing function. Okay. So that curve, that function is going to follow the direction of the slope. I have an upward slope, I must be having an upward function. What's happening between negative 1 and 1? It's decreasing, right? We can see that negative slope here on the graph. What would be a good number to test if you didn't have the graph? Yeah, if we test x equals 0, and we put x equals 0 into the derivative here, 3 times 0 is 0 minus 3, we get a negative value. And so we know we have a decreasing function. And we have an x cubed function, so we're always kind of cognizant that we might have a plateau. In this case, since we go from increasing to decreasing, we don't. We know we have a hill or a valley. Okay, so we know we have a function going up, transitioning from up to down. That's what that means. So if we transition from up to down, we must have a hill. And then what happens at x is greater than or equal to 1? So if we test x equals 2, and throw 2 in here for the derivative, you get another positive value.
Attention,
And so we'll be
any
increasing in
student
that
who
area.
participates in DECA or Girl Talk, please report to the auditorium for your yearbook photo. Thank you.
Okay, so we have that tangent line that switches back to positive. Okay? Okay, so the idea now is then if we look at this, we should have enough information to try to sketch the derivative. Okay? So what are our derivative values? Like if we look at the function, what would be some really quick, easy derivative values to pick up? Well, the derivative is what? Yeah, where the derivative is 0. What are those values? Where's the derivative 0? Yeah, negative 1 and 1, exactly. So we know that the derivative here is 0, and we know that the derivative here is 0. So if I am graphing those values, then I need to come here to x equals negative 1 and graph a value of 0 and graph a value of 0. I know that at negative 1, my derivative is 0. And what's happening now on either side of those points? What's happening in this area to my derivative? So if we come up to the graph here and look at those tangent lines, are the tangent lines positive or negative? They're positive. So if this is the graph of my derivative, where are my positive values in my graph? Yeah, they're up here above the horizontal axis. So I know I have values up here. I have positive values for my derivative in that region. Now let's look at this next region here, from -1 to 1. If I look up to there, up in the function, and I look at my tangent lines, are my slopes positive or negative? Negative. So where are my negative values on this derivative graph here? Yeah, so I'm really, when I'm graphing a derivative, I'm saying, you know, relative to the axis here, these are my negative derivatives values, and these are my positive derivative values. And so if I have the negative values, I'm here. And what happens to my derivative values? They start at what number and they end at what number? At this location up here, 0. At this location down here, 0. And so I've got to start at 0, and I've got to end at 0, which means I've got to come back to that same location. So I must have some sort of turning point in that region. And then this last region, my derivative values are again positive. So when I try to sketch that derivative, I try to sketch something as smooth as possible, because we do have a continuous function, we know it's differentiable. So it's going to be something smooth. And so I can just kind of go over those points that I sketched in with something as smooth as possible. Does this shape make sense? Knowing that our function is an x cubed? Yes. How come this makes sense? Because this function looks like an x squared, exactly, a parabola. So it looks like x squared. Do we know for sure that the vertex is right there? Could it be lower? Could it be higher? It could be. We don't really care. When they say sketch, they're not looking for correct locations of these turning points. They're just looking that they're on this right spot. Like this turning point should be on this axis. Okay, they're just making sure that they're on the right values for x. Okay? So it should look something like that. How are we doing so far? Okay, knowing this is the derivative, and if we just look at this as like something x squared, like Trent said, does this derivative itself have its own hills and valleys? Right? So this derivative itself has its own critical points. That's what we're going to look at today. We're going to look at the fact that this derivative itself has its own hills and valleys. And what does that mean in terms of the shape of the original graph? So when we're talking about when we're talking about looking at the fact that the derivative has its own hills and valleys, that's what determines the shape of the curve. And so the curve really falls into two basic categories. And those two basic categories are called the concavity or the concavity of the curve. And so whenever we have something that looks like, and somebody brought this up first hour, I thought this was pretty effective. Whenever we have something that looks like a frown, we call that concave down. Okay, in other words, when we say a frown, what we're really saying in calculus words is,
attention students, if you participate in the principal's advisory, and if you participate in the diversity club, please report to the auditorium for your yearbook photo. Thank you.
What we're really saying when we're looking at a concave down is we're saying that this tangent line goes from steep to flat. So if we look at the slope values, a flat slope is what value? 0. And so we're going from this slope here that's nice and steep and positive to 0. What we're saying is that slope is getting smaller. It's decreasing. And so when we have that decreasing slope, we have something that's concave down. Okay, when you have something that's getting flatter and flatter and flatter. Okay, if something is getting steeper and steeper and steeper, and people were thinking of this and saying, well, that looks like a smile, we call that concave up. So as it goes from being a flat value to being more and more vertical, that is defined as concave up. So we start to see that smile. Okay. So let's take a look at our function. Do we have a definite frown part? And do we have a definite smile part in our function? Yes, no? Where's the frown part? Where does it approximately start and approximately end? What part of that function looks like it's a frown? Okay, so maybe starting at -2 and going to where? -1? Okay. Okay, so starting here, and if I stop there, I'm kind of halfway through it, right? And so Trent is saying, well, really, that whole thing could really be looked at as a frown. Does that make sense? Right? Frowns look like this. What about a smile part of the graph? Where might that look? What parts of the graph might look like a smile? Yeah, okay. So starting here and going to where? Like that. That kind of looks like a smile. I agree. So let me just change the properties on
Students
this
who are
a
part
little
of
bit.
the
It's
Athletic
transparent for me.
Advisory Council and Spanish Club, please report to the auditorium for your yearbook photo. Thank you.
I guess I can't make that transparent. Oh, there's no transparency. Okay, so so if we look at the frown as being the green thing, and the smile being the blue highlighted area, let me just kind of bring that to the front. Guess that didn't work so well. Let me just see if I can change this. Opaque, it doesn't look like it. Okay, I guess I can't change it. If we look at that frown being the green and the smile being the blue, knowing that there's a little bit of blue behind there, they overlap a little bit. And if they overlap a little bit, then we got a little bit of ambiguity. We've got to kind of figure out where that frown ends and where that smile begins. Okay, and so we're going to look back at this definition. Concave down, the derivative is decreasing. So decreasing means moving how on the number line? What direction? Okay, okay, so if we start out with a positive value, decreasing is moving towards 0. Do we stop at 0? We keep going into the negatives, and do we stop once we hit the first negatives? We just keep going and keep going and keep going. So we're moving what direction? Towards negative infinity, or maybe to the left, something like that. So a decreasing derivative means we're moving to farther and farther into the negative values. So if we look at this, we start with a positive derivative. Is my derivative value moving towards 0? It's moving towards 0. Is it still moving into the negatives as I turn that corner? Okay. And then what happens is as I go down this part of the function? Okay, so at some point we stop moving towards the left into the negatives and we start moving back out of the negatives. Where is that transition point? Where do you think it is?
Midpoint of the diagonal on the
Yeah, so we have to start to look at what's happening in the middle here as we transition from these negative values that are really steep to these negative values that start to flatten. Okay? And so that is that location where the frown ends and the smile is going to begin. And we call that an inflection point. It's where our trend changes. It's where our tangent lines, as they're trending more vertical, they stop doing that and they start to trend more horizontal. Okay? And so that inflection point is where we officially stop our frown and start our smile. In other words, we change our concavity there. So we change that concavity. We're no longer, this is a as we're going in this green area, this is a decreasing derivative until this point. And
Attention
then the
students who
derivative starts
participate
to
in the Art
increase.
Club and Orchestra, please report to the auditorium for
Okay.
your yearbook photo. Thank you.
Oh, losing the that's quantities. Okay? So we're going to look at that analytically with this function. So if we're looking at how the derivative changes, then we're looking at the second derivative. Okay? We're looking at that rate of change of the first derivative. And you know that every time you hear the phrase rate of change, you know you're talking about a derivative in itself. So we're talking about the rate of change of derivative, we're talking about the derivative of the derivative. So if we come back and look at this function, and what I did is I just drew the derivative. That was our sketch a few pages ago. So this derivative, 3x squared minus 3. I just threw that sketch down there. That location of that that turning point right there is actually accurate. Okay, I just graphed it. If we look at this derivative, does the derivative itself have means and maxes? Yep, this is definitely a minimum for the derivative. Okay, what does that mean for the original function? Where is this minimum for the derivative? Where is that over here on the function? Okay, I agree. Where's that physically on the function graph? It's right here, yep. Okay. There's where that derivative value has a minimum. Okay? And so that's our point of inflection. Okay? And so what we're really saying is, what is the slope of this tangent line? What's the slope of this tangent line right here? It's 0. But this is the derivative graph. So we're looking at if we say slope, we're looking at the derivative of the derivative. How many derivatives do we have then? The derivative of the derivative is taking the derivative how many times? Twice. So that's why we call this the second derivative test. We're looking at the derivative of the function. Okay? And we're setting that equal to 0. We're looking at where that value is 0. And that's going to be our inflection point. That's when our tangent lines stop trending one way and start trending the other. These tangent lines go from steep negatives to flattening out negatives. So what is the second derivative? This is the first
Attention
derivative.
students who participate in ignition or who participate on the senior board.
What's
Please
the
report to
second
the auditorium
derivative?
for your picture. Thank you.
The acceleration, which is going to be 6x.
Okay. So the second derivative is 6x. Alright, we're going to take a derivative of this. We're going to set it equal to 0. What value of x? You solve that, you got a value of x equals 0. Okay. So there's that point of inflection. So what we're going to do now is, now that we're looking at how that derivative is changing, we're going to actually create another organizational table. Okay, focusing on this location, this point of inflection. And so here's this second derivative table. And so at x equals 0 is where we have that point of inflection. That second derivative equal to 0. So what's happening on either side of that point? If we look at it graphically, what's happening over here? Concave up or concave down? Smile or frown? Concave down, right? We've got a frown here, starting from, get my highlighter back out again. Starting from here, going to here, we definitely have a frown. Okay? So let's take a look at that location. So we're talking about, we can use interval notation, we can use an inequality. So I'm going to use an inequality, x is less than or equal to 0. What is the sign of the second derivative? So in other words, if the second derivative is 6x, and we plug in something like -1, what's the value of the second derivative? We plug in -1 in for x, what's the value of the second derivative? -6. Positive or negative? Okay, this is negative. And the second derivative is negative. Then we have concave down. On the other side of that point of inflection, what do we have? Concave up or concave down? In this area? Smile or frown? Smile, so it's concave up. Makes a U as well. So when we look at x is greater than or equal to 0, we have a second derivative. If we stick in +1, we get a second derivative that is positive. So we have a concave up. Okay. So when we look at the whole function, what we like to do is we like to summarize it with all of this information in one table. So we have to actually transition all of these points, these critical points this inflection point, we gotta transition it all the way down to the bottom table, and then summarize these statements in each one of those intervals. So if we transition all of those points down, we have, we use yellow here. We've got an x equals -1. We've got an x equals 0. And we've got an x equals +1. So I've transitioned all those points down. X equals -1, x equals 0, x equals +1. And then I can look at the behaviors. So these behaviors here are just the first derivative test and the second derivative test results. So when I'm in this interval, x less than -1, am I increasing or decreasing? Increasing, and am I concave up or concave down? So I'm increasing and I'm concave down. Okay? So what does that mean in my function? That means my function is going up in value, but it looks like it's part of a from. Does that make sense? Okay? If I'm between 0 and 1, and I said that wrong, sorry. If I'm between -1 and 0, if I'm between -1 and 0, am I increasing or decreasing? Because I'm right here in this area. And am I concave up or concave down? Concave down. So I'm decreasing and I'm concave down. I'm shortening up concave down by just saying CCD. Okay. So my function's getting smaller and I'm still on that frowning part. And then in the next interval from 0 to 1, so I'm right here, increasing or decreasing? Decreasing, concave up or concave down? Concave up, so I'm decreasing, I'm concave up. So my function's getting littler, but I'm starting to be on the smile part. Okay. And then for everything bigger than or equal to 1, am I increasing or decreasing? Decreasing, concave up or concave down? Yep. So I'm increasing and I'm concave up. So my function's getting bigger and I'm on that smile part. Okay? So when we...
Attention students, if you are a senior with a GPA of 3.5 or higher,
class.
you would have received an email on Sunday from Ms. DeYoung and a reminder email this morning from Ms. DeYoung. Please report to the auditorium for your yearbook photo.
Awesome.
If you are a student with academic honors and have achieved a score of 30 or higher on the ACT, please report to the auditorium for your yearbook photo. Thank you.
It's not even Howard. It's not even, is it true?
Yeah. Okay, so really using the first and second derivative test to get the summary table. And then I'm just going to give you some work time because there's really not a whole lot we're going to